A maintenance technician walks across the factory floor for a routine inspection. They step onto an unexpected puddle of machine fluid, slip, and fall. The immediate reaction from management is usually swift and highly predictable. They blame the person. The assumption is that the worker was careless or ignored safety procedures, so the official response is to mandate retraining. Reacting this way creates a dangerous trap. Punishing the worker only addresses the surface symptom of the event. It ignores the hidden variable that actually put the fluid on the floor. If that puddle remains unaddressed, retraining the human will not solve the problem. The hazard is still there, and an accident is likely to happen to someone else. This chart shows the stark difference between a controlled environment and a chaotic one. On top is the stable, predictable process line. Below are erratic, unsolved variation spikes. Notice the red exclamation points marking recurring failures. They are symptoms of unseen, disrupting factors. When obvious methods fail, organizations need a structured operational blueprint to map out these unseen factors. This is where the Fishbone, or Ishikawa, diagram comes in. Using this visual framework shifts the focus from individual blame to the actual mechanics of operation. To build the diagram, we start by defining the exact, measurable problem. That effect goes into the red box at the right, the head of the diagram, anchored by a central spine. This circular matrix shows how teams map the broad ecosystem contributing to that problem. They draw major ribs off the spine using the 6 M's: manpower, method, machine, material, measurement, and Mother Nature. Using these specific categories prevents tunnel vision. Here on the left side of the diagram, the brainstorming phase fills in the details. Teams generate specific sub-causes and attach them to the relevant main branches, like inspection training under method or inspector under people. This complexity often leads to the divergent trap. A team might identify dozens of potential causes and try to fix all of them at once, which can quickly stretch their time and resources too thin. To bypass this trap, teams use multi-voting techniques. By consolidating their opinions, they isolate the single most critical anomaly to investigate further. In this visual map of our case study, the multi-voting process led the team to bypass the people branch. Instead, they flagged a specific equipment leak isolated under the machine category. This cross-section illustrates the next step. The Fishbone maps the horizontal landscape, but to understand this specific machine leak, the team switches to a vertical descent tool, the 5 Whys. We execute the first layer of questioning. Why was there an oil leak? Because a seal had deteriorated. Why had the seal deteriorated? It was too weak for its application. The descent continues. Why was the seal too weak? Because the purchasing team bought a cheaper seal. Why did they purchase a cheaper seal? At the bottom, we hit the real answer. The supplier's service manual failed to specify the required seal type. By pairing the broad scope of the Fishbone map with the precise drill of the 5 Whys, the team successfully bypassed the obvious human scapegoat. They unearthed a hidden, systemic documentation failure. If management had stopped at their initial assumption and simply retrained the employee, the machine would have kept leaking. By updating the supply chain manual, the leak is engineered out permanently. This highlight reflects a core principle of the framework, the belief that many operational failures are systemic, not individual. Once a localized discovery like this is made, it can be integrated into the facility's larger digital maintenance systems to prevent similar failures across all production lines. Manufacturers who master the Fishbone diagram identify the root causes of isolated accidents to re-engineer their ecosystem for predictability and flow.